Okay, ladies and gentlemen, it's just ticked over 11 a.m., at least in my time zone, 7 a.m. Pacific's time zone, or whatever time it is, wherever you are in the world. Just once again, hey, thanks for joining us for our webinars at Ascendo Reliability. We really enjoy not only talking to you, but getting your feedback in terms of how you're experiencing some of the concepts that Fred, me, and other people talk about. It helps us understand what we need to do to fill in our knowledge gaps as well. So it's a two-way street. So today, this webinar is all about what a root cause is. And before I get into too many details about what a root cause is, I'm actually going to go through an example or a case study. And that case study involves what we call bullet-resistant vests. If my computer ever permits me to move to the next slide. So a bullet-resistant vest looks like this. In this case, this is a Zylon bullet-resistant vest. Now, Zylon is a high tensile fiber. So we have a lot of bullet-resistant vests, which a lot of people perceive or assume to be very hard, and that is often the case, where you have a combination of fibers and ceramics. And ceramics are wonderful. They're very, very strong in compression, so they do a great job of deforming an incoming round when it hits that bullet-resistant vest, making that round deform and therefore impart force over a bigger area, which reduces the local pressure. The problem with those sorts of vests is they're not very flexible and they're not breathable. They don't allow moisture to get from the inside to the outside, which is a very big deal for soldiers, sailors, airmen, and police officers. And so we have these types of vests as well, these very flexible vests, which are made exclusively from high tensile strength fibers. The problem with that is these fibers, because they're all flexible, aren't particularly good at deflecting or deforming those incoming rounds. They need to be extraordinarily strong. And in this case, this bullet-resistant vest was made from Zylon fiber, very, very strong, which is related to Kevlar in a way. And the Zylon bullet-resistant vests are manufactured by this company called Second Chance Body Armor. And the fibers themselves are manufactured by a Japanese company. And the idea is that these bullet-resistant vests would then help all sorts of people in risky forms of employment get through their day, for lack of a better term. But unfortunately, in 2003, one of these Zylon vests had a round go through it. Unfortunately, in that case, the police officer was injured, but he was not killed. Unfortunately, very soon after this incident, another police officer was shot. The round did penetrate the vest, and he was killed. And anyway, the ensuing investigation, they determined that in that vest that was penetrated, Zylon fibers were 30% weaker than they should have been. And when they tested other Zylon vests that had been used across law enforcement agencies across North America, they found that 58% of these Zylon vests were penetrated by rounds they were supposed to defeat. 38% had excessive back face deformation, which means that the rounds weren't penetrating, but they were essentially deforming the vest too far into the body of the police officer, which is also very dangerous. And unfortunately, that only meant that 4% of these vests were okay. So something was going on. And so we need to look a bit in greater detail on what is going on when these bullet-resistant vests function well. And so here we have a cross-section of a bullet-resistant vest with the fiber weave made up of these very strong fibers. We have the incoming round over here. And when that round hits our vest, the first thing it does is deform. We call that mushrooming. And of course, if you've got a ceramic vest, which is rigid and hard, mushrooming is much more pronounced. So there is some mushrooming when it hits a flexible bullet-resistant vest, but there's not as much. It's not quite nearly, not a lot when compared to those really hard bullet-resistant vests. And what happens is that when that round hits that bullet-resistant vest, it creates what we call a shear plug. And essentially, it just starts punching a hole. through the fiber weave. And that's okay. That's what the fiber weave is supposed to do, because every time we have another layer of fibers that essentially fracture, that absorbs energy. And not all of these fibers are able or should be able to form part of the shear plug, because at the back we want to make sure that there's enough fibers which don't form part of the shear plugs. They deform and they too absorb energy through delamination. And this whole process creates this what we call conoid shock wave, which goes through the vest and reflects and otherwise dissipates energy across the entire fiber weave. The end state is that we would expect to see a shear plug with broken or fractured fibers at the back, all of which is absorbing energy and therefore preventing the round from penetrating. And so we obviously want really strong fibers. The stronger the fiber, the better. And fibers typically don't come much stronger than what we call these PBO fibers, which is polyphenylene benzobisoxazole fibers. We're going to call them PBO fibers for short, or better yet, we'll call them Zylon, because that's their trademark name. And so these fibers are very small, and they're made up of actually lots of little fibrils. And so we have what is quite a complex or complicated structure, lots of little microfibrils, and we have a surface sheet, and somehow we're able to make these fibers at a very small scale. Problem is that when we expose these fibers to water, something really bad happens. And because these are polymers, we want our molecules, these really long molecules, to stay essentially connected through these covalent bonds. But when water comes along, that really ruins our day. So this is a really zoomed in version of the PBO fiber that makes up Zylon bullet resistant vests. So whenever water comes along, these H2O molecules, this oxazole link, which has got 3 carbon atoms and 1 nitrogen and 1 oxygen atom, it essentially goes through 2 steps. The first step is it unlinks on one side. The second step is it unlinks on the other side. And each of those unlinkings needs a water molecule. So we want to make sure that water doesn't get anywhere near our Zylon fibers. And when they were manufactured, they were supposed to have water-resistant coating. Anyway, so when they're investigating these Zylon fibers, these bullet-resistant vests, which were failing due to these Zylon fibers somehow being weaker than they should have, the National Institute of Justice did some testing. They got some Zylon fiber and they put the Zylon fiber in an environmental chamber at about 55 degrees Celsius, which is a relatively high temperature with 0% relative humidity. And over time, you can see if this testing went on for almost a year, you can see that there was a relatively small reduction, if any, in terms of the tensile strength of our Zylon fibers. But that was not the case when they added humidity. And you can see how quickly the residual tensile strength of Zylon fibers degraded over time when there was, in this case, around between 37% and 60% relative humidity. And when they took that most of that humidity out of the environment, so it went down to 5% relative humidity, while there was still a decrease in tensile strength, it seemed to slow down a lot. So there was clearly a problem with our Zylon fibers. And obviously, when you're a police officer or a soldier, sailor, or airman wearing a flexible vest, you're sweating. And so you're creating water every step, every single second. And that's water will, in this case, degrade Zylon fibers. Thing is, Second Chance didn't test for this well-known hydrolysis phenomenon. In fact, it's one of the better case studies in terms of how whistleblowers are treated in Western legislative frameworks, because there was a couple of internal bells rung within Second Chance body armor. The options included addressing the problem head on or trying to bury it. And of course, they tried to bury it, and they ignored their own test results and eventually declared bankruptcy when they were forced to recall Zylon-based vests. Now, Toyoba themselves, the organization which manufactured these Zylon fibers, they didn't cover themselves in glory either. In fact, it was a 13-year pitched legal battle they fought with the US government. In the end, they had to pay a $66 million fine. Now, of course, there's only one known death from these vests, but the chances are there's at least some more injuries at the very least. And it all comes down to root causes. How do we make things reliable? If we know this is how our Zolan fibers are going to react, if we know what the root causes of that failure are, that gives us a fighting chance of being able to design those failures out of our system, or at the very least control. And so we use this term root cause a lot in reliability engineering. And that means anything to all numbers of people. So while this statement is true, if we understand the root causes of failure, we will then be able to do things which would probably prevent this Zylon bullet-resistant vest fiasco from ever happening. But I'll just open it up to you guys. If anyone's brave enough to share in the chat window what they think the root cause of failure is, I'd love to hear your perspective, because that concept is what we're going to be talking about for the next hour or so. So let's see if anyone has their own idea. Well, I know you do have your own idea. Let's see if anyone's brave enough to share their idea of root cause with the rest of our attendees. Okay, so I got a very specific response. Moisture was not part of the original functional specification. So that's a root cause for our bullet-resistant vests. And I can completely, I can acknowledge that is a very valid potential root cause. Moisture was not part of the original functional specification. I like that for a couple of reasons we'll come back to. I suppose my question though, and this is my bad, what is a root cause in general? If you were to open up the textbook that is your mind, or you are trying to explain to someone what the root cause of failure is conceptually or philosophically, what would a root cause mean to you? Anyone willing to share what they think a textbook might say a root cause is, or what you think a root cause is? Maybe that's why we're all here, to talk about root causes. Maybe we're here to learn what a root cause is, at least from my perspective, and the way that I think will help. I like Brian's proposal for a root cause, because he talks about something a human being did or didn't do. So hold that thought for a minute. Let's have a look at an example where we are trying to understand the root cause of potential failures for this smart lock. And yes, smart locks are wonderful devices. They're entering the market in greater frequencies every single day. And obviously smart locks are made up of lots of different parts and components. And we can sometimes get wowed with smart technology to the extent that we might overlook some of the more simpler reasons for failure. I need to go back because I see Mark has come back with an idea of what a root cause is, which is any cause which, if controlled, has a potential to mitigate the risk of an issue occurring. I like that one too. So we'll come back to these definitions when we talk about what a root cause means in a way which I think is very, very helpful. So if we go to our smart lock, and let's say Mark is trying, amongst others, is trying to control whatever it is that's going to result in failure. We're early development stages here, so we're trying to get ahead of the curve. We're trying to understand root causes of things that are likely to occur but haven't reared their ugly heads yet. What can we do? Well, like I said, we can't get too enamored with all the smart technology, because at the end of the day, perhaps the most important components of our smart locks from some perspectives are these ones here. The electric motor which drives that bolt in and out of the door jamb. So we often forget about some of the really simple things when we design something new and amazing, such as cables or wires that join circuit boards and electrical components. So think about your smart lock, which is supposed to operate in lovely homes. There's no angry children or teenagers going through stages. And essentially, the door doesn't get slammed a lot. But we know That is rarely the case. We will often come across users who, for whatever reason, slam that door or do things to our system we don't always naturally anticipate. And if we have a door which is slammed shut a lot, just think about what it could do to these solder joints for these loose wires. And then what we want to do as reliability engineers is get to the root causes of the, or potential root causes of these of this failure, because when we do that, we can come up with these wonderful things called corrective actions. So for example, corrective action number one was to use thicker gauge wire to make sure there's better better adhesion, I should say, provided by the solder joint at the motor. Corrective action number two was to have shorter wires to limit the free swinging mass. And correction action number three was to physically restrain the wires, so the momentum associated with slamming that door was transferred through shock loading to the case of our smart lock and not to the solder joints. Corrective action number four was to take solder out of it entirely at the circuit board end, and we use a socket and plug assembly, which also makes it that much easier to assemble. Corrective action number five is visual inspections of incoming motors from our suppliers. We're going to perhaps look at a small number of our incoming motors and make sure that soldering was done to a high enough standard for that surveillance testing. Maybe we even go one step further, and for a even smaller fraction, we might look at 10% of incoming motors and conduct automated microscopic optical inspection. So these are wonderful corrective actions, and the design corrective actions essentially cost nothing if you pick them up early. If you're able to incorporate thicker gauge wires and these case clips as part of your first design, I know there's an inherent cost in having slightly more material, but in practice, you and I both know these really simple design ideas are almost negligibly expensive if we think about them from the very start. And that is how we make reliability happen. We make reliability happen by thinking ahead, trying to prevent all these failures from occurring, because we are smart enough, because we're smart enough to design something that can work. We should be smart enough to work out how it might fail. And when we bake reliability into our system, it means that these wonderfully simple, trivial design characteristics, which become part of our first design, don't add nothing to our budget, and of course they actually shrink our schedule, because these are failures that we're preventing from observing during our first prototype testing, which means we're able to focus our efforts on other, perhaps more sophisticated ways of our thing failing, I should say. So what is reliability? We are all reliability engineers, but it's worth going over this one more time to make sure we're all on the same page. What we just looked at, anticipating the root causes of failure and coming up with corrective actions to address them, is how we make reliability a thing, how we bake reliability into our design. But reliability itself, as we all know, hopefully, is a probability that an item will not fail for a designated period under specified conditions. Now, this definition sucks because it includes the term probability, and we hate the term probability as engineers. We like things or scenarios where for a set of inputs, we get the same outputs no matter what happens. When we talk about probability, of course, we are talking about randomness, and failure is frustratingly random. The second part of this definition is that our thing is not going to fail. The third part is that we need to understand that this changes over time. As our things get older, more damage accumulates. And so we need to think about periods over which we're expecting our thing to not fail, or at the very least, to have a relatively low probability of failing. And we need to measure our designated period in terms of usage metrics that make sense to our failure mechanisms. And last but not least is specified conditions, which is how a user or customer interacts with includes how our user or customer interacts with our system. And so reliability is something that's going to change over time, which is why we often see reliability expressed with a reliability curve that starts at 100% and goes down over time. And so, for example, here we have this probability of failure, or which implies a 50% reliability at this point in time. And as we, or usage, I should say, and as we continue using our system, the reliability goes down until we essentially have a 100% chance of failure. So reliability is a measure of how often failure occurs. And failure is a product of causality. That means one thing causes another, and that causes another thing, so on and so forth. And so failure is the event where a system inherently ceases to perform a specified or required function. And function is a very key word here. To understand what a failure is, you need to understand what functions your system is supposed to provide. Now, a function is a behavior, process, action, or task. It's quite a broad definition for obvious reasons. In essence, a function is what your system is intended to do. Now, there are different types of functions, and we can get very caught up in system engineering labeling, which is very important in certain environments. But we want to keep things really simple when we are using our brains to design something. We want to look at this as an aid to brainstorming, because essentially that's what design is: brainstorming wonderful ideas of creating a wonderful new thing and trying to work out the best way of moving forward. But because of that, we want to categorize functions in a way that will help us human beings work out what our system design should be. So functions often start with some sort of input. Not all functions, but sometimes our system needs something to provide a function. And that is usually energy. So if you need something which is going to provide torque, for example, perhaps the energy source comes from a power supply. So if the power supply is offline, it's the motor it is driving, it hasn't ceased being functional. It's just that the input required for that function has been taken away. Now, our favorite form of function is what we call a basic function, all about performance. And there's plenty of, went too fast. There's plenty of examples on the screen right now. Is it supposed to transform? Is it supposed to secure? What is our system trying to do? And this is a very natural type of function that we engineers and technicians and technically minded people latch onto. But then there are these wonderful functions called interface functions. And these are the functions which allow components to interact with other components in our system. So, for example, a lot of spacecraft have failed because one component was talking in terms of foot-pounds, another component was talking in terms of Newton meters when they're both referencing torque. And because there are different units, and one component was expecting units, that variable in unit A, and instead of got it in terms of unit B, all of a sudden the control of that spacecraft was lost. And we need to remember that interfaces are a vital part of not only the components within our system, but how our system interacts with the world around it. And as a rule, we expect 50% of failures to occur at interfaces. Then the other sort of function are those functions that we as engineers tend to gloss over, the additional functions. The things we say are nice to have. Is it easy to maintain? Does it look good? Is it comfortable? Does it have a nice user interface? Now, the reality is additional functions are way more important than we give them credit for, because if you as a customer are looking on the shelf for two seemingly comparable products, the one which has better additional functionality, which looks better, which is aesthetically pleasing to the eye, which is lighter, for example, or has an easier user interface, that's the one that they're going to purchase, even if it is just as functional in terms of those basic functions as a competitor. So these are the different types of functions, and breaking them down into these categories helps our brainstorming juices. And so that helps us work out what a failure is, because functions are the most important element of the failure definition. So failure is the event where a system inherently ceases to perform a specified or required function. So because failure is a random process, and we just said failure involves a random process, and the failure itself is an event which is an outcome of that random process, we have to look at these things in a very particular way. So this apple here represents the outcome of something like a failure event. Our system can't do what it's supposed to do. And yesterday it was working fine, but today it's not. It suffered a failure event. And this is what this apple represents, a bad thing. I love apples. I love in particular all sorts of red apples, like delicious and all sorts of other things. So this is just an analogy and not a damning sentiment against apples. Just using this as a tool to help represent our failure process. So because this is an apple, it has to grow on a tree. So we call this tree the tree of failure. And we have different types of failure represented by each one of these different apples. But for these apples to be the same size is a bit misleading, because we know that some failures matter a lot more than others. And knowing that helps us prioritize our effort. Remember, reliability engineering is not about over-engineering. It's about efficiently working out what the vital few things or weak points of our system are so we can get rid of them. And that starts with understanding what failures are in terms of how badly they affect our value proposition. Now, a simple way of dealing with these failures is to remove the tree, which is wonderful, but because the root system of the tree still exists, the tree grows back and it has the same fruit the next season. This is what a lot of organizations try to do. The reason being is because it is simple and it doesn't involve you getting dirty. Getting dirty means you go into the ground to find that root cause. Now, the root cause can be embarrassing. It can mean that you need to do something fundamentally or culturally different. We need to perhaps have a good, long, hard look at ourselves in the hall of mirrors and say, this thing we've been doing for years, maybe it's not the best way of doing it. And that root cause, at least philosophically, then we'll go through different steps and cause different events on a chain reaction sort of approach all the way up until our failure event, which is our apple growing on this tree. But again, our little representation isn't quite complete because there are lots of different ways, lots of different factors that drive failure. There's typically no such thing as a single root cause. So because of that, because the name root cause implies a certain level of singularity, some textbooks, for example, will call these different roots causal factors. They need to combine in a way to create failure. If you remove one of these causal factors, you will have some reduction in prevalence, but there may be there's enough other causal factors that failure will still occur. Which brings us to the concept of root cause. Now, a root cause is the initiating cause of failure, at least according to several textbooky sort of documents out there. And this, unfortunately, tells us nothing. Remember, what we're trying to talk about today is a framework which helps brainstorming, which helps you practically identify the true root causes of whatever's going wrong. So I want to scrub out this definition, and I want to say that I want to emphasize that a root cause is the thing that we can change to make sure that failure hardly happens again. And because it's something we can change, as a rule, a root cause is a behavior. So for example, Brian proposed that for our Xylon bullet resistant vest earlier in this lesson, a potential root cause was that moisture was not part of the original functional specification. That is a root cause. Our lack of attention to detail for this original functional specification, or perhaps not investigating the use case well enough, those are human behaviors, and therefore they are root causes because we can change behaviors. In fact, behaviors are the only things we can change. And so that means that a lot of root causes look like these human beings. Now, for those of you who have done any of my courses or my webinars in the past, I like introducing the 3 enemies of reliability. The first one is the infant manager, whose favorite catchphrase is WTF, which stands for the wrong thing fast. He wants it yesterday, he wants it really cheap. And of course, If that creates lots of problems later on the line, ideally it's going to be in someone else's budgetary report or in somebody else's department. He or she doesn't care. He wants progress today. Doesn't matter what that means in terms of long-term atrocities. Then the second enemy of reliability is our ponderous professor, the person who, for whatever reason, gets a kick out of doing reliability stuff, theoretical reliability stuff, academic reliability stuff, and not practical stuff that helps you work out what the next step of your design process needs to be to create something that's very robust, that's going to work for a long time. So that's enemy number two. And enemy number three is our process zealot, who doesn't care how you do it as long as it complies with standard X, Y, Z. And even if it's done, even if your familiar or root cause analysis or fracas is terrible, as long as it ticks all the boxes, this person is happy. These are quintessential root causes of failure, because these enemies represent a set of behaviors which are always competing with good reliability performance. So these are what lots of root causes look like. And that makes root cause analysis in many cases very challenging, because it asks us as an organization, whatever organization we're part of, to look at what we stuffed up. And that is very challenging because we need to be humble. So a root cause, in a way, is always your fault. Now, that's a very negative connotation. There's a way we can rephrase that to make sure we have positivity on our documentation, on our reports. But if we try and apportion blame to somebody else, that won't change a thing. So for example, we're going to go back to the electric motor and the circuit board of our smart lock. And we're trying to go back to the scenario where we just realized that the door slams are going to wreak havoc on our design as it stands today, because we've got simple wires which are connected with nothing but solder joints. And solder joints should not be structural. So what we want to do when we are faced with this realization, ideally we've identified this problem early. If we haven't, perhaps we've had some failures during initial prototype testing. Whatever the case might be, we are going to try and look at our tree of failure, where one of these fruits corresponds with some failure we've since either envisaged hypothetically or observed through prototype testing, or perhaps observed because our customers have submitted warranty claims, and we want to work out what the root causes of this particular failure might be, remembering that root causes are something you can do something about. Now, if we just simply blame the manufacturer or blame the supplier, this is avoiding responsibility. If you can't do anything about that, then essentially this factor becomes environmental. It's not a root cause. If you're just saying it's a manufacturer's fault and just complain bitterly about those manufacturers and then walk out of that office and then do nothing, what you're implicitly acknowledging collectively is that this is an environmental concern. We can't change the quality of our manufacturers, but we're going to pretend it's not a thing. However, if we look more internally and say, well, perhaps we put too much time pressure on our supplier. Perhaps we didn't establish a collaborative working environment. Perhaps we didn't specify correctly. Perhaps these are things that we could have done better. Then this is where you start to improve reliability, where you eat that slice of humble pie, look at what you perhaps could have didn't do well in the past or can do in the future to mitigate this problem. Then now you're talking about making reliability happen. So a really easy way of finding a true root cause from a very reliability engineering based perspective is to ask the following simple set of questions. Now, when I teach this sort of stuff, and I've done this in the past, I've tried to template textbook definitions of reliability concepts into these questions. And it doesn't work, at least not easily, because there's so much confusion about what should be fairly consistent definitions across the industry. So what I tend to do these days is get rid of textbook definitions and replace that with the intent of what most textbooks are trying to suggest. And beyond that, replace it with an intent to get to the true root cause, the purpose of making something better. And when I did that, this is what I came up with. So the first thing we ask ourselves when we're faced with failure, either hypothetically or through direct observation, is ask ourselves, what is my system doing / not doing as part of this failure event? The next question we ask is, why did this happen? Now, the why did this happen bit is essentially the trunk of our tree. What were the steps that connect our root cause to the failure event? Why did this thing happen in a very physical way? And the reason we need to do that is because if we don't ask ourselves, why did this happen, we will never work down, get down to our root cause. And the root cause is something we can do something about. And we break this question down even further into 3 different sub questions, which is what broke, how did it break, and what started it. And that I'll go through a couple of examples very soon. And when we get to our root, this allows us to ask ourselves, what did we do wrong? If we know what started this reason for our thing failing, we should be able to come up with an answer to this question: what did we do wrong? Which is very negative, I know. So we can sometimes replace that with, what do we need to do in the future to prevent this failure from occurring? And this is where the reason why we're breaking this down into these really simple questions is because we're all about brainstorming and reliability. Brainstorming sounds very general and very, very vague, maybe abstract, but brainstorming is at the heart of many activities, such as a failure mode and effect analysis. And this is where the facilitator of a FMEA is going to organize brainstorming to work out what the potential root causes of failure might be. And if she or he follows these steps, we'll all but guarantee we get to the true root cause. Or perhaps this is a facilitator for a root cause analysis. And again, if we get hung up on textbooky definitions, so people are wondering what that word means with that 15-syllable acronym over there, 15-syllable acronym. Anyways, what these complex terminologies might refer to, they spend too much time looking at their notes to get on top of definitions, as opposed to simply working out what happened. So if we look at our smart lock again, so now a smart lock is a wonderful device which allows us to enter or pass through doors when our smart lock can, it allows that door to be unlocked when it realizes our smartphone is in our pocket within a couple of meters or a couple of yards proximity, so it automatically unlocks. There are many ways our smart lock can fail. And we're going to revisit our electric motor, because our electric motor is at the heart of smart lock operations. Even if the circuitry can determine that we're supposed to unlock the door, if that motor is not working, then our smart lock is practically useless. So for our little motor here, and my computer's trying to keep up, let's just say we're in the middle of a FMEA or a FMECA or some other brainstorming session where we're trying to get ahead of the curve. We realize through whatever means this particular area of our system is a concern. And then we ask ourselves, what could go wrong? And we often start with getting our functions correctly defined, because with our functions come the definition of failure. So in this case, the function is to convert 6-volt 100 milliamp DC to rotational kinetic energy with torque and speed specifications to be determined, because we're at the preliminary design stage. We know we need to specify those the torque and speed. Haven't got there yet, but we know it's going to come. So the first question we might ask ourselves is, what is my system doing or not doing to realize this function? And that's where we brainstorm and come up with all sorts of different explanations. And one of the first things we come up with might be that the shaft won't turn. So our facilitator is doing a brainstorming session, lots of different ideas. One of them is that the shaft won't turn. So we look at that particular phrase, that shaft won't turn. The next question we ask ourselves is, why did this happen? Specifically, what broke? And our facilitator does some more brainstorming, and one of the things they come up with is shaft fracture. So let's look at shaft fracture. Next question we ask ourselves is, how did it break? Of course, we have all sorts of different possible explanations. One of them could be fatigue cracking. Okay, so the next question we ask ourselves after we focus on fatigue is, what started it? Well, there's lots of different ways that fatigue can start. Surface imperfections, defects, misaligned bearings and gears. Now, by asking ourselves these questions in this very systemic way, we all but guarantee we think of all the possible ways our shaft won't turn. And when we do that, we get good coverage for our potential root causes and corrective actions. So go back to these questions we just asked ourselves. What is my system not doing? Why did this happen? What broke? How did it break? What started it? What did we do wrong? What do we need to do? All right. So those last two questions, that's where the rubber hits the road. What do we need to do to prevent this particular form of failure from occurring? Well, let's just take the answers to all these questions and write them in these boxes. So that fruit at the top, which represents one of the ways our thing might fail. Well, the shaft won't turn. And then we start putting our answers into a phrase. Due to shaft fracture from fatigue cracking caused by surface imperfections. Now, when we write it like this, we have what can't it do anymore, what broke, how did that happen, what started it. It really makes sure that everyone in that room is on the same page and will almost certainly come up with some really useful targeted corrective actions to make sure that those surface imperfections are not going to cause failures in the future. And that could be as a proposal to conduct a process from here which focuses on manufacturing to ensure that there are no surface cracks that go deeper than 0.05 millimeters. And so this little phrase that we came up with in these orange boxes is what we call a root cause statement. When you do it this way, at least in my experience, when you follow the bouncing ball, you all but guarantee you get to a meaningful root cause statement, which helps your team come up with corrective actions that will actually work and not some broadly dismissive test regime or guidebook this or do something in accordance with standard that. We are now coming up with some useful corrective actions to make sure that this failure of all failures will never occur. So if you get the root cause statement right, you will find the root cause. But that said, there's no absolutes in anything we do, because sometimes it's okay to do a shortcut. So let's go back to our smart lock motor, and we're asking ourselves, what could go wrong with this little part of our system? So we look at our functions. Of course, there's plenty of functions for our smart lock motor besides this function here, but let's just focus on this one again. What is my system not doing? Or perhaps in our brainstorming session, our facilitator convened a conversation with one of the potential types of failure was that our shaft will still turn, but it's now turning too slowly. Okay, so this is something we're going to focus on when we ask our questions as we go down towards our root cause. So why did this happen? Well, question number one of that part is what broke? Well, we have reduced electrical contact conductivity, which means that we have the right voltage being supplied, the right current being supplied, but for whatever reason, we're losing conductivity. There's a lot more resistance than there should be in our electrical contacts. And of course, there's plenty more explanations for why our shaft is turning too slowly. So let's focus on this potential explanation. How did it break? Well, perhaps it was through corrosion. We come up with lots of different ideas again, and one of those brainstormed ideas was corrosion, where our contacts are oxidizing. And the next question we're supposed to ask is, what started it? Well, our facilitator might stop right there and not ask ourselves that last final question. We'll come back to that. Why our facilitator might be happy in doing that. So here are our questions. What is my system doing / not doing? Why did this happen? What do we do wrong? What do we need to do? So let's just put our answers into our little orange boxes again. Our shaft turns too slowly due to reduced electrical contact conductivity from corrosion, and we, for whatever reason, our facilitator omitted the final, asking ourselves the final question, which is, what started this? Well, this still allows us to come up with some useful corrective actions. In this case, we might review the use case because humidity extremes are obviously going to play a part in corrosion. We all know, remember, we all know that humidity and moisture causes corrosion, and maybe conduct a design FMEA on the housing seal itself. So our shorter root cause statement looks like this. Our shaft turns too slowly due to reduced electrical contact conductivity from corrosion. Now, the reason why, in this case, our amazing FMEA or RCA facilitator omitted that final question, which is, what started this, is because in this case, this facilitator was able to survey the room, and he or she knew that this team was all across corrosion. There was not a lot of benefit to be gained from examining corrosion in greater detail. Perhaps these guys and girls have been dealing with corrosion their entire professional lives, and the reason why we want to ask ourselves questions is to brainstorm. But we typically only brainstorm when our brains aren't full of truth. We're trying to work out what might cause certain things. But if these guys are corrosion experts, all we need to do is say corrosion, and they go, oh, well, I know how to fix corrosion, and that's fair enough. It's up to the skill judgment, I should say, of the facilitator to work out where and when it is okay to stop. In fact, it's sometimes okay to go even shorter than those, ask even fewer questions than the questions we just asked ourselves for our corrosion-based failure. So back to our electric motor. What could go wrong? Our function to convert 6-volt 100 milliamp DC to rotational kinetic energy. Question number 1, what is my system doing / not doing? Brainstorm all the potential ways our thing can not live up to expectations. Re-examine shaft turning too slowly. And that brainstorming session where we identify lots of different ways or lots of different things that could potentially break, instead of electrical contacts corroding, we came up with a failed bearing. So in this case, our facilitator says, okay, say no more. I don't need to ask any more questions. And if we go back to those questions that we're supposed to ask, or at least I'm saying could help, or you as a guide, these questions could help you get to the true root cause. In this case, we have only answered the first two. Our shaft is turning too slowly due to failed bearing, and we haven't gone any further than that. And that, again, is okay. And in this case, and we'll talk about why very shortly. So some of the potential corrective actions are that the use case is reviewed and to identify the anticipated cycles in bearing specifications. So we're trying to work out how many times the inner race of our bearing needs to rotate from our use case. Once we do that, we can perhaps do things like incoming alt testing of 5% of all incoming motors to make sure that the motors we're getting from our suppliers are going to last the journey. Or perhaps if this is part of a system FMEA and you don't know electric motors very well, you could say, you know what, we need to conduct a design FMEA on this particular motor or bearing or whatever component is relevant. So our root cause statement is now a lot shorter. Shaft turns too slowly due to a failed bearing. Now, the reason why our facilitator said that was okay in this case was, again, because he or she surveyed the room and he or she knew at least that everyone in that team, or at least a fair portion of the people in that team, knew bearing failures inside and out. If we know essentially the causal chain once we get to a particular answer of a question, and if we have the experts in the room, we sometimes don't need to ask all those other questions to get to the true root cause. If you've got the bearing guy sitting right there, they should be able to tell you the top 10 ways that bearing is going to fail, the top 10 faults, the top 10 failure mechanisms, the top 10 root causes, And all of a sudden we have some wonderful corrective actions because this person knows bearings. So this is a brainstorming tool which you need to employ judiciously. But if you've got nothing, if you're truly stumped about what the true root causes of your system are, then asking yourselves all these questions is the way to go. Because that will all but guarantee, if you ask those questions sequentially, especially if you go down as far as asking yourself what started this, you will get a very seamless logical transition from your failure all the way down to the root cause. And so we measure how good this brainstorming session is by essentially asking ourselves what has come out of this session. So I need to fix this right here. Got an issue with my computer. Always have issues with my computers during webinars. So the question we're asking ourselves is, how do we measure how good our root cause taxonomy is? Well, if we go back to our FAMIA or RCA facilitator, the outcomes or the outputs of the activity that she oversees is measured in terms of the coverage and the quality of our corrective actions. And so even if you only go through half the process, or even if you use your own process, you know that you have done this process well of identifying potential root causes through the coverage and the quality of your corrective actions. So your corrective actions need to cover the vital few ways your thing can fail, and they need to correctly address the true root cause such that if you implement that corrective action, that root cause is not going to happen again. And so it comes all back to this tree of failure and these questions we are asking ourselves. At the top, we have the first and foremost question: what is my system not doing? And at the bottom, we have, what do we need to do? That bottom question, or the answer to that bottom question, is the reason why we do this stuff. Now, for those of you who've gone, that's great, but I do need to have some academic formalism with this stuff. We're asking ourselves some very low-level questions. I might understand these questions that you're asking me. They're very simple language. But where are the failure modes? What are these failure mechanisms? What are all these other terms I hear about in textbooks? How do they come into play when we're talking about this tree of failure? Well, each one of these questions aligns with a particular reliability engineering term. So for example, our first question, what is my system doing or not doing? That is what we call a functional failure mode, the functional consequence of our thing not working. And there's lots of different examples you can see on the screen now. Intermittent speed, complete fluid loss, does not transmit torque. So you can see the answer to this question involves no physical explanation of what we're doing or what has happened. It's all about the function we have lost. And the reason why we want to take it this slowly and ask ourselves what might go wrong functionally is to preserve the brainstorming logic. If we go down too fast, too quickly, we don't branch out into all possible explanations, which is brutally important when it comes to reliability engineering. So the first step is asking ourselves what might go wrong functionally. So what is my system not doing? The answer to that question is a functional failure mode. Now, the functional failure mode allows us to assess the severity of that failure mode. That tells us what the effects are going to be, and it helps us work out what the vital few failure modes are. That's the first question. It's all about the functional failure mode. The second question is, why did this happen? And we start with asking ourselves what broke. And the answer to that question is what we call the physical failure mode, the physical consequence of a failure mechanism. And there are some examples in the slide right on the screen right now. And so this is where we explain what the physical state of our component is that meant that we don't have that function anymore. So we go down one more level of investigation and describe what is wrong. Something has fractured, something is loose, something is sticking. The next question we ask ourselves, if you remember, is how did it break? This is the failure mechanism, the physical, chemical, electrical, thermal, or other process which results in failure. So for example, this is a failure mechanism here, a tin whisker, where for whatever reason, for reasons we don't completely understand today, if we have tin plated terminals, we have these little tiny whiskers, which for some reason go from one terminal to another, creating a short circuit. Another example of a failure mechanism is dendritic growth. And so if we have any scenario where we have a cathode or an anode, we have these little lightning-like metallic crystals working from one side to the other. And when it reaches the anode, we have a very small short circuit. So this is a failure mechanism. Another failure mechanism is corrosion, where we have something that oxidizes. Another failure mechanism is fatigue, where we have cyclic stresses contributing to a crack growing incrementally over time. So these are all failure mechanisms and potential answers to our question of a question that asks, where we ask, how did it break? The next question is what started all this? And that is what we call a fault, the immediate cause of failure. And that fault could be stress concentrators, where we have sharp angles in our geometry, which raise the stress locally, which means that's where fatigue cracks are going to emanate from. Or we might have defects in our metallic structure, which again increases localized stresses and will then be a likely initiation point for a fatigue crack. And of course, there's lots of other defects and impurities and things that are going to create the right conditions for the failure mechanism to continue. But if we go through the process of asking yourself sequentially, what went wrong, what broke, how did that happen, what started it, we get to this lovely root cause statement, which helps us answer the next question, which is, what did we do wrong? And that's the root cause. The root cause is a behavior. You can't change what has already happened. You can't take that impurity out of the metal. The root cause is our poor quality manufacturing techniques, or our neglect to consider impurities when specifying the outputs of our manufacturing process, or not doing appropriate inspection or incoming testing. If we didn't do those things, those are potential root causes. We can't change physical phenomena that have happened in the past. The only thing we can address is our behaviors, which leads us to the main reason we are doing all this, which is to identify corrective actions. Now, corrective action is also known as a fix, and it involves a change to a system design, operation, maintenance procedure, or the manufacturing process of the item for the purpose of improving its reliability. So that is why we need to understand what a true root cause is. If there's something we can't address, then it's not a root cause or a potential root cause, because it can't be coupled with a corrective action. Even if your manufacturer is doing something untoward, the corrective actions you can influence range from better relationships with your suppliers through to incoming inspection or better specifications or incoming testing. These are things you can change, and therefore can be coupled with a true root cause. But if you're not able to address it, then it's simply an environmental characteristic you need to deal with. And all this comes down to this thing we call the reliability mindset, which comprises of this whole overarching concept of value, language, and methods. Language is very important, because if we don't know what we're talking about, or if I use the term failure mode and it means something to me and you think it means something else, we are just wasting our time. When we have these competing ideas of definitions, they impose these hurdles to efficient and effective brainstorming. And so language is brutally important, because at the heart of reliability is this failure tree. So the first thing we need to do with our reliability tree of failure, I should say, is that through a well-defined concept of value, work out which apples are bigger than others, which failures matter the most. And when we identify these failures that matter the most, we're able to work out by how much they matter. What is the cost of this failure occurring? Then comes language, which is what we talked about today. I've all but given up on trying to use failure modes and failure mechanisms and faults in a ubiquitously unanimous way across the industry. there are so many different and competing ideas about what a failure mode and a failure mechanism and a fault might be. So when I do this, I simply keep it in terms of those questions I just went through then. That very simple terminology, where we're not relying on everyone to have a textbook recollection of these definitions. And when we do that, it really accelerates the brainstorming process. We make sure we focus on the things that matter. Everyone knows what we're talking about because we're using simple words and asking ourselves simple questions. At the end of the day, we get much better root causes that address the corrective actions, which address the vital few root causes. And when we do that, we add the most value to our organization based on our system performance. You can see here, we haven't eliminated all the apples. We just got rid of the big ones. And already that looks a lot better. In fact, we have more apples. Sorry, we haven't removed the majority of the apples. We only took 4 apples out, and we have 7 apples left. So we still have more apples left than we took out. But because these are smaller apples, our tree looks a lot less imposing. And that's what happens when we do great brainstorming. We're using terminology and questions that make sense to everybody. We get rid of, or not get too focused on the textbook definitions of reliability concepts, and all focus on coming up with relevant corrective actions which address the vital few. That is the reliability mindset. So, are there any questions, comments? Does anyone have their own experiences when it comes to causality and what root causes are, and perhaps how root causes have been misused over the journey? Are there any questions? I can see a preemptive response. Thank you, Bartholomew, for that compliment. I assume you had to leave. Thank you, Duke. Much appreciated. Any questions or any war stories or any additional observations? Thanks again, Volker. Okay, so I'm more than happy to stay around for a little bit to answer questions if they're taking a little while to ferment. But if I could really reinforce that we as reliability engineers can sometimes get too caught up with textbook definitions, standard definitions. Speaking with our friend Carl Carlson again the other day, Fred, and we shared similar stories where I think Carl was talking about how he had to sit for over 45 minutes listening to a bunch of different people debate what a fault means, or what the definition of a fault was. And that was 45 minutes for the times by how many people were there that you will never get back in terms of lost productivity, all because people get too fixated on what those terms mean. So it's been my experience that you can jettison the terms, break it down to simple questions using simple words, and if necessary, convert those answers back into the textbooky definitions after the event. You get more good, you get more corrective actions, you get more benefit from that activity. So any more for any more? I still see a few people are hanging around. At risk of being ponderous, risk assessment is useful, i.e. the probability of occurrence. Completely agree with you, Pete. Risk assessment is an important part of working out those vital few, and I don't want to downplay that. In fact, you can't do this without doing risk assessment. That's not what I classify as a ponderous professor, to be clear, Pete. I'm talking about that ponderous professor who loves doing certain 5-parameter Weibull distribution analysis that takes 2 years to get an answer back, where we actually need the answer next week in terms of which vendor we're going to go with. Are we talking about those ponderous professors who rather characterize or measure measure reliability as opposed to giving us best guesses in the next week or so to help us make better design decisions. And hopefully, you know what I'm talking about there. But doing a robust risk assessment does not mean you are a ponderous professor. Far from it. That's usually a good activity. Any more questions or comments or observations? All right, Fred, I think we're good for today. Jacob has asked, my apologies, went too soon. Should we include the question how often this occurs? And the answer is absolutely. So when I used an example of a FMEA facilitator, a FMEA facilitator is the sort of person who's going to be asking what might happen in the future, what are the potential root causes of that thing that might happen in the future, for the purposes of identifying corrective actions today. Now, a FMEA, which is an entirely different webinar in its own right, will always involve characterization of occurrence. If you're doing it for MECA, you try and characterize the failure rate. And it is they're not parameters, those occurrence or frequency scores will inform things like what we call a risk prioritization number, or RPN. And the RPN then goes on to define how big or small our apple is. And so, yes, absolutely, coming back to Pete's point again, a risk assessment, which includes severity and occurrence and perhaps other things, is a vital tool for us working out how big or small our apples are. And yes, I'll completely agree with you, Jacob. We should always include how often this thing occurs in working out the size of those apples. Thank you, Brian, for that feedback as well. All right, I went a bit too early last time, Fred. We'll just maybe wait a couple more seconds to see if any more messages or questions are coming through before we call it quits for today. I think we're good. So again, if there's any further questions, you've got my contact details because you're able to find this webinar through Ascendo. But if you do want to reach out and even just have a general conversation about this sort of stuff, please feel free. Always enjoy engaging with the visitors of Fred's Ascendo website. It's always a good conversation. But again, thank you for your time today. And I look forward to speaking with you guys or whoever wants to attend for my webinar for next month.